Hello, ladies and gentlemen, and thank you for joining me as we finish off part one of our 2017-2018 Alberta Math Contest with question 16 here. How many positive integers n can be found so that the product of all divisors of n, including n, is 24 to the 2040? Okay. So n has to divide this number, and 24 is kind of nice. 24 is 2 cubed times 3. It's 8 times 3. But 24 to the 240, using our exponent rules, would be 2 to the 270, 3 to the 240. Now, n has to divide this. So n has to look like some power of 2 times some power of 3. If there were a power of 5 anywhere in there, well, you'd need to have a power of 5 in the product because n has to divide this. And for a moment, imagine we only had powers of 2. Well, then the factors of n, the divisors, I guess they call it, of n would only be powers of 2. And then you multiply all those together, you wouldn't get this. Because where are your factors of 3 coming from? So n's got to look like this. Now, what are the factors of n going to look like? Well, divisors, I guess they call them. Same thing, divisors, factors. The divisors have to look like two to some power, j to some power, although these ones can have no factor of 3 and no factor of 2. In fact, 1 is a divisor of n. Okay? So how are we going to multiply these all out? What are we going to do here? Let's look at a smaller case. Okay, let's look at something like 2 cubed times 3 squared. Okay. Can we write out the factors there? Well, this number is going to be 8 times 9. This is 72. The factors of 72 are 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, and 72. Now, when I multiply them all together, one thing we might notice is that if I group the powers of 2 together, I could also group powers of 2 multiplied by a single 3. So we're just being very particularly organized. And this sort of technique that I'm using also works if you were going to do something like, say, add all the factors. You want to group based on the factors that are similar. So these are the ones, let's put them in red. These are the ones that only have factors of 2. These ones are 3 times a power of 2. Then we have 9 times a power of 2. And that's really going to be it. You can't have more 3s. Okay? But watch what happens when I take out the 3s, and there'll be 4 3s I can take out of here because there are 4 of these. Okay? I get 1, 2, 4, and 8. And then how many 9s can I take? Well, each one of them has a 9, so we get 9 to the 4. 1, 2, 3. Or 1, 2, 4, 8. Okay. And technically, you're bringing out 1 out of these if you want to keep the pattern the same. But you'll notice, you can pull out a certain number of each power of 3. And then how many of each? Well, we've got a certain number of each power of 2. Now we've got 3 1s. Then you've got 3 2s. 3 4s. And 3 8s. Why 3s and why 4 for the powers of 3? Where are these coming from? Okay. Well, how many times would 8 appear? Well, 8 could appear with no 3, 1 3, or 2 3. So the fact that the biggest power of 3 is 3 to the 2 means that you could have 0, 1, or 2. That's only going to be 3 possibilities. And that's why we get 8 3 times. Okay? Same reason we get 4 3 times. If you're going to have 2 to the 2 and 3 to the something, there's only 3 possibilities, 0, 1, or 2, for what you could have here. Same with 9. How many numbers could have 9 with them? It's got to be some power of 2 times 9. Well, you could have 2 to the 0, or 2 to the 1, or 2 to the 2, or 2 to the 3, but we can't have 2 to the 4. We don't have 4 2s to play with. Okay? So what are we going to have? Well, if I have something like 2 to the A, 3 to the B, we're going to have, in our product of divisors, we'll have A plus 1 of each power of 3, and B plus 1, so 0, 1, 2, all the way up to B, of each power of 2, right? So we'll get 1 to the B plus 1, 2 to the B plus 1, 4 to the B plus 1, not 5, 8 to the B plus 1, and we'll just keep going all the way up to 2 to the A to the B plus 1. And then we'll also have 1 to the A plus 1, 3 to the A plus 1. Keep going all the way up to 3B to the A plus 1. Okay? So now I know at least a little what this product should look like. But we can do a little bit better. I can take out B plus 1 here. And take out A plus 1 here. And now I just need to find the product of this many powers of 3. And these sequential powers of 2. Okay? So what are we looking at here? Well, we're looking at something, I'm going to be a bit more general. We're looking at a single prime. 1 is p to the 0, p to the 1, p to the 2. But when you have things of the same base, how do you multiply them all out? Well, you add their exponents. So 0 plus 1 plus 2, all the way up to plus k. And there's an expression for the sum of these first k natural numbers, because the 0 doesn't really matter. K times k plus 1 all over 2. This is a very useful expression, and if you are not aware of it, I would recommend you know it for upcoming contests. Okay? It's just the sum of the first k numbers. So 1 plus 2 plus 3 plus 4 plus 5 is the same as 5 times 6 all over 2, which is true. It's 15. Okay? So now my product of divisors looks like, so the powers of 2 all the way up to what? 2 to the A. So that'll be A times A plus 1 all over 2. And that got raised to the B plus 1. And then all the powers of 3 multiplied together, 3B times B plus 1 all over 2. The A plus 1. Now we can sort of expand this out. A, and I'm going to particularly focus on the A plus 1, B plus 1 over 2, and 3B, A plus 1, B plus 1, all over 2. Oops, keep touching the top there. Okay. So that's kind of interesting. And if I were to do something like let x for exponent be a plus 1 times b plus 1 all over 2, what we've really got is 2 to the x to the a, 3 to the x, or no, I guess, here's what we could do. This is 2 to the ax, 3 to the bx, but if I take out the x from both of them, you get this. Now what does this look like? This looks like n. So n to the x is my product of all these factors. So 24 to the 240 has to look like n to the x. Okay. So 24 to the 240 how can I figure out what possible x's we could have? Okay. Because as soon as I figure out an x, that sort of fixes what this is going to be. Of course, once we decide on x, is there necessarily an a and b that could make this work? Remember, a and b can't be 0. So you can't just say, oh yeah, double. I suppose as long as you let a be 1, b be x minus 1, that would work. So I guess it doesn't really matter. You can always, as soon as I find an x, I can get an a and a b that work. Okay, fine. So if that's the case, well, then what could x be? And we're going to use this expression here, and we've already cleaned up n to the x, 24 to the 240. We've already cleaned this up into 2 to the 720, 3 to the 240. Now, n is a positive integer. We're raising it to the x power, whatever x happens to be. Right? And x will be an integer. Right? It does have to be an integer. Oh, maybe it might not have to be an integer. A times a plus 1 over 2 is an integer, and b plus 1 is an integer, but who says a is necessarily a factor of that? If a is even, we might have a problem. Yeah, if a is even and b is even, we might not have... Ah. Okay. I'm going to let a plus 1 times b plus 1 be y. X is y over 2, and it's entirely possible that this is not an integer. So n to the y over 2. So we would be raising n to the power of y and then square rooting it. So let's square both sides. N to the y is 2 to the 1440, 3 to the 480. Okay. Y is necessarily an integer. X wasn't. It was entirely possible, I think, that x could not be an integer. That's feasible. Okay. So n to the y, but if I've got... So this over here is a perfect yth power. That means, based on our prime factorization, y has to divide 1440, and y has to divide 480. So what values could y be? Well, y could be anything as long as it's a factor of both of those. So what's the GCD, the greatest common divisor, of these two? Now I know that they've got 240 in common. So we can take that out, and then GCD of 3 times... Actually, we can take out a factor of 480, can't we? Oh, 480 times 3 is... So, okay, GCD is 480. So y can be any factor of 480. 480, and then that should, in theory, produce an a and a b, as long as y is not prime. Okay, because if it was prime, then one of these has to just be 1, and so a would be 0 or b would be 0, but then, as I've already said, you wouldn't get the powers of 2 and 3 that you need. Okay. Okay, so 480 has... That's 16 times 30. That's 2 to the 5, 3, and 5 there as well. Okay, so anything other than, I think, 1, 3, and 5 should do the trick. So there's 5 plus 1 times 3, 1 plus 1 times 1 plus 1, so that'd be 6 times 2 times 2, 24 factors. Don't include 1, 2, 3, or 5. So that should be 20 possible y values that aren't prime. So there should be a plus 1 and b plus 1, both of them greater than or equal to 2 to make my y. And then you get your sort of x like this. And then I'm just thinking ahead. I think 6 squared would be a good example to go through in a moment. 20 possible values of y. And so each y tells me an n. Because as soon as I know y, the yth root of this expression gives me n. And now we just go back and check. 20 is a... Oh. Now that's a bit more interesting. 0, 1, 2, or 3. 20 is definitely not amongst these. So what, if anything, have I done wrong here? So those expressions are fine. Actually, let's double check. So if I wanted to do something like the product of all the factors of 12, we get 8 times 18 times 12, so that's 18 times 96. So we get 1728, which happens to be 12 to the power of 3. Now, how does this work with my particular... And, oh, okay, I think that's it. My choice of y makes an n, but y determines the a and b in 2 different ways. Okay, that's a bit more interesting. Anyways, getting back to this, so our expressions work. 12 is 2 squared times 3 to the 1. So I should get 2 to the, it's a first, right? 2 to the 2 times 3 times 2 all over 2, and 3 to the 1 times 3 times 2 over 2. So I should get 3 to the 3, 2 squared, or 2 to the 6, which is this number here. Okay. So I think instead we're going to have to go with 2 to the a plus 1, b plus 1 over 2, 3 to the b, a plus 1, b plus 1 all over 2. Oops. So this is my product of all the divisors, and this is 2 to the 720, 3 to the 240. And now whatever this is, If if we call this x, then x the rooting both sides, we can see this. We're still going to get this nice ratio. A has to be 3 times b. So I think that might be important. So a is 3 times b, so what we've really got is 2 to the 3b, 3b plus 1, b plus 1, all over 2. 3b, 3b plus 1, b plus 1, all over 2. And this has to be 2 to the 720, 3 to the 240. And so now we could try and solve these. And as long as I solve one of these, for b, we get our a. So how many solutions are we going to have? There we go. It looks like we might have 3 solutions, and this certainly works a lot better. Multiply by 2, so we'll get this is 480. Okay. Is there a particularly nice way to go about doing this? 3b cubed plus 4b squared plus b minus 480 equals 0. I guess. Is there anything else we could do here with this? Well, b has to be bigger than 0, definitely. I can't divide by 3 or anything like that. I don't see an easy way to factor this. Can we experiment and try and find something? So I know 480, because I just did this, is 2 to the 5, 3 to the 1, 5 to the 1. One of these has to be a multiple of 5. Definitely can't be 3b plus 1. Maybe b is 4. 4, 5, 13. No, that wouldn't work. We could try b as 5. 5, 16, 6. Yeah, that works. So I know b equals 5 is a solution. And now we can do polynomial division to get that out. So we need something in the middle. So minus 15b squared, b and b, and so this should be 19. And minus 95b oh, this should be plus 96. There we go. All right. So that's nice, and now I can just ask, does this have any integer roots? And I don't think so, but we'll do a quadratic formula. Well, we'll just check the discriminant. So 19 squared minus 4 AC. So this will be 19 squared is 361, and this is already almost 400 times a 3. This is going to be less than 0, so no other roots. So only b equals 5, and so only one value of n. N would have to be 2 to the 15, 3 to the 5. So that's the only one that should work. And I suppose if we wanted to, we could double check. 15 times 16 times 6 is going to be all over 2. So that's going to be 3, so that's 48 times 15, or 24 times 30, so that is 720. And then 5 times 16 times 6, all over 2 should be 240, because we just divide by 3. So yeah, that works, and there's only one And that does the trick. So there we go, B. So I do apologize for that mix-up. I forgot for a moment y was determined in two different ways, or A and B are determined two different ways by y, and so we need to eliminate that. And there we go. So just one for our possibilities, and that wraps up the whole contest. All 16 questions done. If you are interested, if you're someone who thinks you're going to do well, if you found these questions not particularly challenging, there is a part 2 to this contest that I believe is invite only for about 50 students. But if you think you might make it, if you think you might be invited, or if you're a particularly strong grade 9 or grade 10 student, you feel free to check out part 2 which, of this contest as well. So less questions. It's a written solution contest, but there's some interesting questions on there. But I think that's it for me for now. Have a wonderful day, and I'll see you for more math in the future.